Our final topic for integration theory is to look at integrals where infinity is involved. These are called improper integrals. It may be that one or two of the limits of the integral are infinity, or the integrand is not well behaved in its domain, such that there's vertical asymptotes in the domain of the function. Let's look at these in turn. Let's look first at integrals with limits at infinity. So let's say f of x is integrable over the range a all the way up to infinity. What does the integral to infinity mean? Well, we define this as the limit as t tends to infinity of the integral from a up to t. So we do the integration as normal. We use the evaluation theorem because t is a finite number, and then we take the limit. We don't just do the integral and plug in infinity. Let's look at the integral of 1 over x to some power p over the range 1 to infinity. Let's just have a quick look at these types of functions. If p is less than 1, it heads off to 0. The function from 1 to infinity, the function 1 over x to the p, tends to 0 as x tends to infinity quite slowly. If p is larger than 1, it tends to infinity fairly rapidly. Let's try and evaluate this for different values of p. So let's use the definition of what I mean by a limit up to infinity using a limit. I can evaluate this integral nice and easily, provided p is not equal to 1. Then this is just x to the 1 minus p over 1 minus p. Evaluated between 1, t, which becomes the limit as t tends to infinity. Now, depending on the value of p, this limit comes out to be different things. So if p is greater than 1, then t to the 1 minus p is going to tend to 0 as t tends to infinity. So this part here will tend to 0 for p larger than 1, and I'm left with 1 over p minus 1. And if p is less than 1, but still positive, this part here is going to tend to infinity. For p equals 1, you need to do this separately because we have a logarithm involved. You can try that yourself. So that's an example of using a limit up to infinity. For limits to minus infinity, it's the same deal. For limits like where we have an integral from minus infinity to infinity, one needs to be really careful not to evaluate these at the same time. What we do is we write, assuming f is integral over the whole range, we split the integral up somewhere convenient in the real line, some point a, and then we evaluate these using limits. So then we write this as, then you can integrate and evaluate as normal. The reason we do that is you can end up in all sorts of problems if you try and evaluate both limits simultaneously. Things might cancel out where they shouldn't, and so on. The second type of improper integral one comes across a lot and often gets wrong are discontinuous integrands. This is a little bit more subtle and you have to be aware that this can happen quite often. Let's start with an example, the integral from minus 1 to 1, 1 over x squared dx. Let's just plow away and try to use the evaluation theorem and see what happens. Let's try and evaluate this as follows. The integral of 1 over x squared is x to the minus 2 plus 1. Naively then, this is 1 over minus 1 minus, which is then equal to minus 2. Okay, so the evaluation theorem gives us a number. Why could that be possibly wrong? How can this possibly make sense when I know that the function 1 over x squared is positive everywhere in its domain? And so this integral, in some sense, is the area under those curves where there's a hole at the origin. That can't be a negative number, so there's something clearly gone wrong. Something is definitely wrong here. And the reason there's something wrong here is that the evaluation theorem relies on the function being continuous over the domain. The function isn't continuous over the domain of integration. You can't use it just out of the box. You need to be careful wherever it's discontinuous. And this is a great example. So we need to split at x equals 0 and evaluate the two parts separately. Okay, so let's try that. Let's try the positive bit first. And in order to deal with this problem at the origin, because the function isn't defined at x equals 0, we need to be a bit careful when we evaluate this integral. So we do this again using limits, where I'm now looking at the integral from t to 1, and then I take the limit as t tends to 0 from the right-hand side. So 0 plus. Now I've written it out like this, the rest is just calculation. And this is equal to infinity, because as t tends to 0, 1 over t tends to infinity. So the integral then is divergent, and it doesn't matter what the other part evaluates to. If one part of it evaluates to infinity, it's all over. The integral is divergent. Let's try a closely related example. Now, again, we can't just write this as log mod x from -1 to 1, which would give me 0. This doesn't work because the function itself has a discontinuity. So we're looking for the integral between this region in here and this region in here. So again, we need to evaluate these two halves separately because the function is discontinuous. We need to see what happens on both sides of this. So let's evaluate the left-hand side. So I write it using the limit as t tends to 0 from the left of the integral from -1 to t. The integral of 1 over x is the log of mod x, which when I evaluate it at the limits becomes logarithm modulus of t. When I let that tend to 0, it gives me -infinity. So that means that the integral again is divergent. And these two areas do not cancel out. You might think that because this area here and this area here must be the same through symmetry, they don't cancel when we're evaluating this integral. It's a really important concept, this, that infinities can't cancel like this. So it seems completely counterintuitive. Why can't infinities cancel? Let's consider the integral from -infinity to infinity, just x. dx, nice simple example. Then this integral concerns these shaded regions. Now, it looks like from the problem that the shaded region on the right is always going to be the same as the shaded region on the left. And for any finite even interval, if it was the integral from -a to a, for any number a, that would be true. They would cancel out and we would get 0 because x is an odd function. But once you get to infinity, it doesn't work like that anymore. So the question is, turns out this is, again, completely the wrong thing to do. Big fat 0 for that answer. The reason is, I could also write the limit in this way. The limit as t tends to infinity from -t to 2t. As t tends to infinity, both the upper and lower limits go to infinity, so why not? If I do it this way, well, and I'm left with an overall factor of t squared, so this is equal to plus infinity. If I'd done the same with the lower limit, I would have got -infinity. And in fact, fiddling around in this way, I could get any number I like doing that. So this is why infinities can't cancel. It doesn't make any sense to do it this way. So the key thing is that you need to split up the integral and then calculate those two limits separately. And in this case, this integral is divergent.